We already derived kinematic equations for distance, velocity, acceleration, and time for the linear case. We can do the same thing for the angular case, and they are put right here in the table so that we can compare what is happening. So there is a very similar derivation, which we are not going to do. But in linear case, in a linear scenario, we had velocity, which was the initial velocity plus acceleration times time. Very similarly, the angular velocity is going to be the initial one plus angular acceleration times distance. We will have, sorry, times time. For the angle, we will have a very similar equation that we had for the distance. And then same thing for the velocity squared and the angular velocity, and then the average and the velocity. Keep in mind that those equations are valid for constant angular acceleration. So that means that alpha is constant, angular acceleration, alpha is constant right here, just the same way that we had A being constant for the linear. With that said, we're going to look at an example. Our example about a centrifuge acceleration, we have a centrifuge rotor that's accelerated for 30 seconds from rest to 20,000 RPM. That is an abbreviation for revolutions per minute, and we will calculate the average angular acceleration, and then we'll figure out through how many revolutions the centrifuge rotor will be turning during the acceleration period, assuming constant angular acceleration. So first of all, we know that the initial angular velocity has to be equal 0, and then we can see that since angular velocity has to be equal 2 pi times the frequency from our last lesson, we know it's going to be 2 pi radians per revolution, and the frequency here is 20,000 RPM, so 20,000, that is revolutions per minute. Since there are 60 seconds in a minute and we have to convert everything into seconds, we have to divide by 60 seconds per minute, which is going to give us 2100 radian per second. Now, because the average acceleration, I don't have it here, because average acceleration is delta omega over delta t, that means that we can plug in, so delta omega, remember omega 0 is 0, so we're doing 2100 radian per second, and then we're dividing by delta t, so the time is going to be over here 30 seconds, and that is going to give us 70 radian per second squared. So what that means is that in every second the velocity increases by 70 radian per second, and we can convert that into radian per second. We can convert that into revolutions per second. We will multiply this by 1 revolution per 2 pi radians, right? One revolution, one full revolution is 2 pi radians, and with that we will get 70 divided by 2 pi. That's going to give us approximately 11 revolutions per second. All right, so that is our part A. For part B, what we have to do is we will have to calculate the angle theta. So it's this formula. Again, omega 0 is 0. So we're just multiplying 1/2 times 70 times t squared. So we will get theta equals 1/2 times 70 radian per second squared times our 30 seconds, and it should be squared. Once we multiply all those, we are going to get 3.15 times times 10 to the power 4 radian. Let's see if I can fit it here. Times 10 to the power 4 radians. That is an intermediate result. To get our final result, because the question is through how many revolutions, right, the centrifuge rotor turned during the acceleration period. So we found the angle. So final thing is we have to take our angle and then we have to divide it by 2 pi radians per revolution. So once we plug in the numbers, we are going to get approximately 5.0. So now the units are right. Times 10 to the power 3 revolution. And that is our answer. Okay. Now, as for the rolling motion without the slipping, so we are thinking about the wheel that is turning, like a bike wheel that is turning while it's moving, and there is no slipping happening. So let's take a look at what's happening in this case. So the rolling motion is actually a combination of two types of motion. It includes both rotation and translation because the wheel is not only rotating in place, it's actually moving. So if we look at the point P right here on the wheel, we can see that the wheel is going to be, well, we see that the wheel is rolling to the right. The center of the wheel moves to the right with the velocity, linear velocity v. The point P right here is momentarily at rest because otherwise we would have slipping. So this way, point P is at rest. Now we can also change the reference frame here, and then we can see that, okay, maybe the wheel is at rest and it's the ground that's moving. So what that means in this case is that um, the point P was here at rest, and now the point P is moving to the left with the velocity that is negative of this one. So it's going to be negative v, velocity negative v, which means that the velocity, our velocity v, has to be in relationship with the angular velocity r omega, just like what we had in our previous case. So this is our relationship. So v, linear velocity, has to be equal r omega, and that works when there is no slipping. Very simple formula. And we will look into an example with the bicycle, which is given to us. It slows down with the uniform velocity, slows down uniformly, means acceleration is zero, acceleration is constant, not zero, constant. Our initial velocity is 8.4 meters per second. The rest it takes for the bicycle to get to rest 115 meters, and then each wheel is going to rotate, or each wheel has a diameter of 68 centimeters. We are calculating the angular velocity at the initial term, at the initial time, and the total number of revolutions each wheel rotates before coming to rest, and finally, not finally, c, an angular acceleration, and then d, the time it took to come to a stop. So four things. All right, so let's start with part A. So we know that since v equals, I'm going to write it here again, v equals r omega. So that means that omega has to be equal v over r. And then we're looking at the initial, the angular velocity at the initial instant. So at time t equals 0. So velocity was equal 8.4 meters per second. And then the radius that's given to us is 68 centimeters. So that is 68, sorry, diameter is 68 centimeters, which can be, so that's the diameter of 68 centimeters. So we have to take 1/2 of 68, and then we have to convert it to meters. So we will have to multiply it by 0.01. So in other words, that whole thing is going to give us 8.40 meters per second over 0.340 meters. Once we multiply it, one divide, we are getting 24.7 radians per second. Part A, done. Part B, the total number of revolutions. So we know that the wheel rolls 115 meters. We know that the full circumference is going to be 2 pi times the radius, which is 0.34 meters, and that is going to give us 53.8 revolutions. Sorry, 53.8 0.8 revolutions, right? So we kind of like cancel the meters, but we have to have that unit, like the placeholder. So revolutions is kind of like a placeholder for the units. For part C, the angular acceleration of the wheel. So for that one, we are using the formula that we had before over here, that we can derive from this one. So it's going to be omega minus omega naught squared all over 2 theta, because we're trying to figure out alpha. And that is, so let me write it down, omega squared minus omega naught squared over 2 theta. So the final acceleration is going to be 0 because the bicycle now is at a stop. The initial acceleration is going to be, the initial velocity, sorry, 24.7 radians per second. That's what we calculated in part A. And then our angle is going to be 2, and then we have to multiply 2 pi radians times 53.8 revolutions, right? So 53.8 revolutions. Each revolution is 2 pi radians. Once we multiply all that, we are going to get negative 0.902, and the units are going to be radians per second squared. 2 pi, sorry, radian per revolution. So that is, oh, forgot to multiply this guy squared. Okay, looked at the units and saw that this is second squared, this is seconds. Yes, so this was squared. Finally, part D, we need to calculate the time it took to come to a stop. So again, let's take a look at our formulas. It looks like probably we can use the very first formula for the time, because we know these the velocity omega, we know the acceleration alpha, and then we can figure out t. So t in this case is going to be equal omega minus omega 0 over alpha. So in this, so again, omega is 0. Omega 0 is 24.7 radians per second, and then we're dividing by alpha, which we just figured out was negative 0.902 radians per second squared, and that is going to give us positive, right? The negatives will cancel out, so the time is going to be positive 27.4 seconds. That's it.